Hi, I'm Peyton Kilborn, and this is my Lab 3 for Physics 2212, all about circuits. So the purpose of this lab is to apply the principles of the loop rule and other aspects of conservation of energy to a steady-state circuit system. Another purpose is to utilize the multimeters to accurately measure both voltage and current. And then, further on, be able to predict the behavior of a circuit that has aspects of resistors and capacitors using Ohm's law. So for formulas that would help us achieve this, we have Ohm's law in that triangle of V equals IR, and that can be arranged to account for any of the different variables. The loop rule of the sum of voltage difference around a closed loop is 0, so all the positives and all the negatives will cancel out, allowing you to find unknown voltages. And then capacitance, which is charge over change in voltage, was also helpful throughout the lab. Alright, so the first series circuit we have set up has two 1.5 volt batteries, 47 ohm resistor, 100 ohm resistor, and these were wired in series along with two different multimeters set to measure current. And then through these, when we started looking at the system, we saw that the resistance was 147 ohms, and at 3 volts, the current would be 0.02 amps. And the recorded from the two multimeters was 19.5 milliamps and then 18.6 milliamps. 19.5 milliamps turns into 0.0195 amps, and 18.6 is 0.0186 amps. So the first number is very accurate. The second number was lesser. However, that could be a difference in like some variation of either error in the machine, it wasn't zeroed correctly, or some kind of user error, or just resistance issues in the wires connected to the multimeter. Don't fully know what caused that. However, it is to the scale where it's not extreme variation from expected. A second circuit was the RC resistance capacitor circuit. Here, we have the same two batteries, the 100 ohm resistor and the light bulb, and the capacitor. As we started this one, we saw the light bulb turn on at full brightness and then dim. And the cause of this was the potential difference was actually decreasing as the capacitor was absorbing charge and not letting charge pass through. So then the delta V started at 3 volts and then fell until the system stopped, and then the light bulb turned off as the capacitor was fully charged. For the what if section of this, what if you charged the capacitor without a resistor in the circuit? How quickly would the charge in the ideal model predict the time for the capacitor to reach full charge? And would this actually happen in real life? So the thing that's getting at is the voltage across the capacitor and charging equation down here. The voltage in the capacitor is the voltage in the system times the 1 minus e to the negative t RC. Okay, so ideal model of just voltage, capacitor, no resistance, R would be 0. So it would be take something to the negative infinity exponential, which turns it into 0. So the voltage of the capacitor would instantly and always be the voltage of the system. So the capacitor would instantly charge it, but however, this is not applicable in real life as everything has some level of resistance, even the wires that we are using. And then that's why our measured time is approximately 2 seconds. So, but in a perfect system, it would be 0. And then we can still get lower, but it will never actually still be 0 because there will be always some imperfect amounts of resistance. Thank you.